Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to your online lecture series of EE314 Measurements and Instrumentation. This is the first lecture of week 11, your lecture number 33. And in this lecture, we are going to discuss about how to transmit the measured signal. And we will discuss the electrical, pneumatic, optic, and wireless methods of signal transmission, and we'll also skim through some protocols that have been developed for digital signal transmission. So let's get started. The measurement signal transmission is chapter number 10 in your textbook number 1, that is by Alan S. Morris. So we'll start with electrical transmission. And the simplest method of electrical transmission, as we all know, is to transmit the measured signal as a varying analog voltage. However, this mode of transmission often causes the measurement signal to become corrupted by the noise. And to avoid such corruption, the signal can be transmitted as a varying current instead of a varying voltage. An alternate solution is to transmit the signal by superimposing it on AC signal, that is called modulation, and we'll discuss it further in this lecture. So transmission as varying voltage lies under the electrical transmission, and it is the most simple one because most of the signals already exist in an electrical form as varying analog voltages, and it is very simple to transmit them as they are without converting them into any other form like current or without any or frequency or without modulation or converting them into optical signals or whatsoever. So transmission as varying voltage without any modification is the simplest way. But as we just pointed out, that there are problems of noise and signal corruption because of the induced noise, electromagnetic interference, EMI, and also the signal is attenuated when it is transmitted over a long distance in the form of a varying analog voltage. So these problems arise and they have to be tackled somehow, and one of the measures to overcome this problem is to amplify the signal and get a high SNR, signal to noise ratio, because amplification will omit the common mode noise and will give you a high SNR, and the shielding of the signal wires against the noise, if you have ever happened to cut through your keyboard cable or your digital data transmission cables, you will find out that there is a wire gauze present on as a shielding against the noise. So all that wire is shielded inside an enclosure of a metallic gauze like this. So that is the shielding of signal wires against the noise, against the electromagnetic noise, electromagnetic interference. Another method that can be used to avoid such issues of signal attenuation and noise is to convert that voltage signal into a current signal and transmit it as a varying current. So what is the advantage of this? Because the current being generated by the current source will be generated regardless of the load resistance. So the load resistance or the resistance of wires will not play any part in signal attenuation. If there is a resistance of the wires and that may act as a load onto your transducer, it will not affect your output current, the magnitude of your output current. So there will be no attenuation. This technique uses currents between ranges of 4 milliamperes to 20 milliamperes to represent the voltage levels of the analog signal. It obviously requires a voltage to current converter that is commonly known as a 4 to 20 milliampere current loop interface, and this is the block diagram of a current to current loop, 4 to 20 milliampere current loop. One thing to note here is that in your textbook, at this point there is written a 4 instead of 0, so that is wrong. The 4 is wrong. I have corrected it here in these slides, so it must be a 0. How it works is that this is your input signal, your varying input voltage signal that you want to convert into current and transmit it over the lines. And we know that we have to convert it not from 0 to any value of a current, but from 4 to 20 milliamperes. Why? I'll come to that. But 4 to 20 milliamperes will be achieved by giving an offset of 4 milliampere current. So here is your one current source I1, and here is your second current source I2. I1 has a constant reference based on which some current will pass through this resistance, and the voltage across this resistance will be a constant voltage. So that constant reference is applied to this current source, and this current source will produce a 4 milliampere current. So this 4 milliampere current is a constant current and it will never change, and that would be an offset to your signal, to the current produced because of your voltage signal. And that voltage signal here is being used as a reference to your second current source, and it will produce a current of 0 to 16 milliampere based on the magnitude of your input voltage. And now this 0 to 16 and this 4 are added to get 4 to 20 milliampere current output. Now, why we need 4 milliamperes but not 0 milliampere? So number one, this 4 milliampere means a 0 V in, but we need to supply power also. So we supply power through this 4 milliampere base current or offset current, and this 4 milliamperes is used to power up the circuit. The second thing is we can use to detect faults if our current at the receiver side is outside this range. So if it is less than 4, we know that there is some problem, some error in the power supply, or as we can see here that the power supply issues are determined if the current is below 3.6 milliamperes, that is the tolerance, and the currents over 21 milliampere are used to detect faults like short circuit. So 4 to 20 is your data range. Outside this is your fault detection. So the current may be less than or more than this range, but your data lies in this range, and your communication signals or your commands lie in the range outside this mentioned 4 to 20 milliamperes. Then there is another method to electronically transmit your signal, and that is because to solve the problem of noise corruption in low level DC voltages, and that is to transfer the signal on an AC carrier before transmission, and then extract it from that carrier at the end of the transmission line. So there are two types of this technique, and this technique is called modulation of the carrier signal. So there can be an amplitude modulation of the signal, and there can be a frequency modulation of the signal. In amplitude modulation, we have a varying voltage signal that results into variations in the amplitude of the carrier wave, and the carrier wave frequency is of several kilohertz. So after shifting the DC signal into a AC carrier, a high pass filter can be applied to the amplitude modulated signal, and it successfully rejects the noise in the form of low frequency drift voltages and the mains interference that is around 50 to 60 hertz. So at the end of the transmission line, the demodulation is carried out to extract that mirrored signal from the carrier. This is the basic technique, that is the block diagram that shows the process of amplitude modulation. So here is your information signal that is in the form of a varying analog voltage, a varying DC analog voltage, but you can also call it an AC voltage, and an aperiodic AC signal with infinite frequencies in that. I'd like to call it a varying DC signal, analog DC signal. Then here is your high frequency carrier signal, and when these two are combined, you get modulation of your carrier signal based on the amplitude of your information signal or the data signal. And it is done by this circuit. So there is a summer, here comes your information, here is your oscillator that generates a fixed high frequency signal, and they are combined together to form an amplitude modulated signal. The second type is frequency modulation, and it achieves even better noise rejection than the amplitude modulation, and it involves translating the variations in analog voltage signal magnitude into frequency variations of a high frequency carrier signal. So here is your signal. Again, you can call it an AC signal, or you can call it a varying DC voltage signal. But this is your data signal. And then this is your amplitude modulation for this signal, for the black signal. If you see here, the amplitude is maximum, the amplitude is decreasing, it is minimum, it is again in the middle, and then again it is maximum. So this is amplitude modulation. But if you see here, this waveform in blue is the frequency modulation, and if you see that the highest magnitude or amplitude of your data signal corresponds to the highest frequency, then the frequency is slowly decreasing, and here at the lowest point of your data signal, your frequency is minimum, your time period is maximum, and then again it goes on. So this is a frequency modulated signal, and the voltage to frequency convergence circuit can be used for this purpose. Then coming to from electrical transmission to the pneumatic transmissions, that is also a way to transmit data from one location to another location. So in recent years, pneumatic transmission tends to have been replaced by other alternatives in most of the new implementations of instrumentation systems, but many examples can still be found in operation in process industries. So pneumatic transmission consists of transmitting your analog signals as a varying pneumatic pressure level that is usually in the range of 3 to 15 psi, and that is similar to the current 4 to 20 milliampere current if you see here. So this 3 psi pressure is just to power up that system. The pneumatic transmission has the advantage of being intrinsically safe, as no one can be shocked by the pneumatic transmission lines, and it also provides similar levels of noise immunity to as compared to the current loops transmission, as we discussed earlier. The disadvantage of using air and pneumatic compressed air as the transmission medium is that the transmission speed is much slower than the electrical or optical transmission. The pneumatic transmission is found particularly in pneumatic control systems where your sensors and actuators or both are pneumatic. Usually both of them are pneumatic, only then pneumatic transmission is preferred. Otherwise, even if one of them is pneumatic, it is converted from pressure into some varying voltage using a transducer, and then it is transmitted electrically or optically. And so coming to the optical transmission. Optical transmission is usually done through fiber optic transmission, although it can be transmitted through air wirelessly, and we'll come to that. But the major thing to note here is that light is used as a carrier of information, not as the medium. And the medium can be an optical fiber or air or vacuum or whatever, but the carrier of that signal is not a pneumatic pressurized air or an electrical signal like voltage or current, but light in case of optical transmission. And light has a number of advantages over electricity as a medium of transmitting information. For example, again, it is intrinsically safe because no one can get an electrical shock by putting its hand in the path of the light. And again, it is immune to the noise corruption of signals by neighboring electromagnetic fields because light is not affected by the EMI, electromagnetic interference. So your interference signals are automatically almost eliminated, just like in case of pneumatic transmission. But the advantage is that it is even faster than electrical signals. So it has the combined advantages of both the pneumatic transmission and the electrical transmission. And the most common form of optical transmission consists of transmitting light along a fiber optic cable. Wireless transmission also exists. Apart from noise reduction, optical signal attenuation along a fiber optic link is much less than electrical signal attenuation along an equivalent length of a metal conductor. That is a very huge advantage. If you have 200 meters or 200 kilometers of a metal wire that carries an electrical signal, no matter in the form of current or voltage, it will have some signal attenuation. But if you have the same length, 200 kilometers of an optical fiber cable, and you transmit the signal in the form of light pulses, the signal attenuation along that line is much smaller because of the very low losses of that medium and the properties of that carrier, that is light. But if this is so ideal, why it is not always used as the medium of transmission? So there must be some disadvantages related to that, and though one of the major disadvantages of that is the cost penalty, because the cost of a fiber optic system compared with the metallic conductors is much higher. And in communication systems, we have to find the feasibility that whether for a certain application, what are our requirements and what is the required data transmission speed, and what is the available budget of that infrastructure development. So that's why fiber optic cables are not always used, but the electrical transmission is still the widest used way of transmission. Fiber optic cables are used for signal transmission in three distinct ways. First, relatively short fiber optic cables are used as parts of various instruments to transmit light from conventional sensors to a more convenient location for processing. Second, longer fiber optic cables are used to connect remote instruments to controllers in instrumentation networks. And third, even longer links are used for data transmission systems in telephone and computer networks. And then these were the wired or connected transmission of the information, but there is also wireless transmission of the signal, and wireless telemetry allows the signal transmission to take place without laying down a physical link in the form of electrical or optical fiber cable. So your system or your signal can be transmitted through air or through vacuum without needing a physical medium. Yes, air will be used as a medium in that case, but you will not use to develop an infrastructure comprising of a medium. You will have to develop an infrastructure to convert that signal into a wireless signal and transmit it into the air or into the vacuum, and the vacuum or air will act as a medium. And at the receiver end, you will have to develop an infrastructure, but between those two stations, you don't have to construct a physical infrastructure comprising of wires or fiber optic cables. And wireless transmission can be achieved using either radio waves or light waves to carry the transmitted signal across a plain air path or a vacuum between a transmitter and a receiver. So there are three forms of wireless telemetry. One is point-to-point telemetry, and point-to-point telemetry uses a very narrowly focused fine beam of light that is usually laser, and that is commonly used for transmission between adjacent buildings, or when the transmitter and receiver are in the line of sight. In the line of sight. So if your transmitter is here and your receiver is here, they have to be in line of sight, and a fine narrow focused beam will travel from this point exactly to this point. If it is focused at this point, the signal is lost. In directed telemetry, though, the transmission is done in a slightly divergent beam of light, and that divergent beam is directed towards even the reflective surfaces such as walls, ceilings, etc. But the problem is that maximum distance is 20 meters. In case of point-to-point telemetry, the distance can be thousands of kilometers. And let me tell you here that this point-to-point optical telemetry is used to communicate with space stations as well. So those are thousands of kilometers away from us. But in case of directed telemetry, the requirement of exact focus of the focus on the target is now omitted, but that comes at a cost of reducing the distance, the achievable distance, dramatically down to 20 meters only. So that can be done inside a closed room. And the most common example is TV remote control. And you would have noticed that even if your remote control is not directly aligned with the receiver of your TV, the channel and the volume can still be controlled. So if it is a bit away from the TV, it is directed at slightly a different angle, the communication is still there. But this distance limitation makes it useless for long distance communications. And then the further going down to the third type, that is diffuse telemetry. It is similar to directed telemetry, but the beam is even more divergent, like this. So this is focused beam telemetry, this is diffuse directed telemetry, and the outermost is diffuse telemetry. The beam is even more divergent. This increases the area of coverage but reduces the transmission speed and range further as compared to the directed telemetry. Then we have radio telemetry using these were all these three were optical. So radio telemetry requires radio waves and it is normally used for transmission over a distance of up to 400 miles. Up to 400 miles, can be used for less than that, and it can be even extended from 400 miles. And this is the basic block diagram you can see right here that is used for radio telemetry, and that is very commonly used for wireless signal transmission. I'm not going into the detail of how this block diagram works. You will study it in your communication systems course, but you will have a data signal, you will have a transducer to convert it into a different form. Then you have a carrier, and you can have multiple carriers of multiple frequencies, and then you have a mixer or a multiplexer, and then of a frequency multiplier, and the RF signal is then transmitted through an antenna. And at the receiver end, all these things are the opposite of what we have at the transmitter end. So there are certain digital transmission protocols that have been developed, and digital transmission has very significant advantages as compared to analog signal transmission, because the possibility of signal corruption during the transmission is greatly reduced, as we discussed, that if you have your analog voltage varying from 0 to 5 volts, you can have a signal of 20 millivolts, and if you have a noise of 10 millivolts, it is 50% of that signal. So your SNR is much reduced, and your signal is not significant anymore. But if you convert this analog voltage into a digital voltage can be either 0 or 1, or this 1 can be 0 volts or 5 volts. So even if this 0 has a 10 millivolt noise and this 5 has a 10 millivolt noise, this 0 will still remain a 0 and this 5 will still remain a 1. So this noise does not affect the digital signals as much as the analog signals. Various protocols have been developed to achieve digital signal transmission, and there are many advantages of using those protocols, because they are secure and they are faster, and they ensure the transmission of signals from the transmitter to the receiver without any errors at very high speeds. So these are some of the examples of protocols that you have experienced or you have heard of. IEEE LAN protocol we are all using in our laptops and mobile phone devices. Similarly, CDMA or GSM is used in telecommunication. the serial UART or USRT you have used in your microcontrollers, and I2C SPI you have used in your sensor interfacing with your microcontrollers or microprocessors, and the CAN interface is usually used in our automobile industry to interface multiple sensing devices with a single processor at over a single line. So there are hundreds of more protocols. We are not going into the details of that, but you can even develop your own protocols, digital transmission protocols, but they must pose some advantages over the existing protocols, and they must not copy the existing protocols. So that's it for the measurement signal transmission. That was mostly related to theory, and to give you an idea of when you have conditioned your analog or digital signals, how you transmit them from one location to another location. And I can even call the transmitter and receivers as part of the signal conditioning circuits. Some may differ from my point of view, but if we see carefully, signal conditioning is happening inside that inside those transmitters and receivers. So you can call it a part of those signal conditioning circuits. Your signal transmission is usually covered in detail in your courses of signals and systems, and then in much more detail the communication systems. So that's it from my side. If you have any questions, you are most welcome to ask me through the MS Teams channel. And till next lecture, see you. Stay safe. Take care. Allah Hafiz.